Well, hello everyone. My name is Steven Bos. I'm a fourth year PhD student from working at Leiden Observatory, and today I will not be talking about the Fast and Furious movie, but I will be talking about the Fast and Furious focal plane wavefront sensing algorithm and how we use this to control the low wind effect at Subaru SCExAO. So first, what is the low wind effect and what is the island effect? And why is it important? Why is it relevant? So the low wind effect is a phenomenon that occurs here at the top ring of the telescope, and it introduces aberrations. And the reason that it is a problem, because the wavefront sensors, the standard wavefront sensors inside AO systems, they have a low sensitivity to these aberrations due to the island effect. So what is the low wind effect exactly? So suppose that you have a telescope structure and we are looking here at the top ring structure. So the top ring structure consists of the secondary mirror and its support, and then the ring holding everything together. It has a certain temperature and it produces a nice PSF. So before observations, the structure is surrounded by air that has the same temperature. But as soon as the telescope dome opens, the telescope structure itself starts to radiate away heat. So the telescope structure itself cools down while the temperature of the air remains the same. So this becomes a problem when you have some wind blowing over your telescope at slow wind, at a low velocity, and this wind, it will hit your spiders, it will rapidly cool down, and then there will be a first temperature step over the spider, and then a temperature gradient over these segments. So a temperature step basically means also a change in a temperature. There will also be a step in refractive index, and a step in refractive index will mean that there will be an optical path length difference between the opposite sides of the spider. So this is a problem because such aberrations can make your very nice PSF look very ugly. So why is this a problem? Because you would say that these aberrations, they occur very close to the pupil, so we should be able to measure these with pupil plane based wavefront sensors. Now the reason that it is hard to measure is because of the island effect. And the island effect is, I think, easiest explained by the Shek-Hartman wavefront sensor. So the Shek-Hartman wavefront sensor places a microlens array over your pupil, and every microlens, it generates a tiny spot, and the position of this spot tells you something about the local gradient of the wavefront. So if you want to do wavefront reconstruction, you basically stitch together all these gradients and then you get an idea of the total wavefront. However, if your microlenses are so small that one spider completely blocks one microlens array, you do not have one single pupil, but you basically have several islands. And within each of these islands, you can reconstruct the wavefront, but there is a problem of stitching together these islands to make it fit. So normally this is not a problem, but as soon as you have aberrations like the low wind effect that have sharp OPD steps over the spider, then you run into trouble because you will be unable to match the OPD step. And I will not go into detail, but the pyramid wavefront sensor also has reduced sensitivity to these kinds of aberrations. So why is focal plane wavefront sensing then a good idea to measure the low wind effect or the island effect? Now, first of all, it has a very strong low wind effect signal because your PSF gets heavily distorted. And as was shown by Olivier Guillon in 2005, it is one of the most sensitive wavefront sensors out there. And the nice added bonus is that it also calibrates any upstream statics that are otherwise inside the reference of your wavefront sensors, and it can also correct for any non-common path aberrations between your main wavefront sensor and your science arm. So the Fast and Furious algorithm is a focal plane wavefront sensing algorithm, and it belongs to the class of sequential phase diversity algorithms. And what it actually means is that it can only run in closed loop because it uses the information of previous DM commands to break any degeneracies in phase estimation. And the nice thing about this algorithm is that it's a software-only solution to focal plane wavefront sensor. So wavefront sensing. You only need focal plane images of point spread functions, and you need control of the DM, and that's enough to run this algorithm. So let's dive a little bit deeper into the wavefront sensing algorithm itself. So we start with a PSF, which is distorted, and we first split it into its odd and even components. With some simple math, we can turn the odd component into an estimate of the odd electric field, and therefore an estimate in the odd wavefront estimate. For the even PSF, the even part is a little bit harder because we can only, with one image, we can only estimate the absolute value of the electric field. So in order to also measure its sign, we need to, so what Fast and Furious does, it uses the previous image with the previously derived DM command that belongs to this image to break this degeneracy and estimate the sign of the electric field. And then together, it will give you the full phase estimation. And what Fast and Furious does, it does this every iteration and just keeps going. So we implemented Fast and Furious at the SCExAO system, which is a high contrast imaging system with an extreme adaptive optics system on the Subaru telescope, which is an 8-meter class telescope on Hawaii. It's behind the AO188 system, which gives a low order wavefront correction. And it features a high order DM and a pyramid wavefront sensor and various science modules in the optical and also in the near infrared. So what is relevant for Fast and Furious is the internal near infrared camera, which is a Zebra 2. That's the camera that we use for Fast and Furious. The DM, there's 45 actuators over the pupil, so we use the SCExAO DM to control the wavefront. And we generally use either the H-band filter, the full H-band filter, or the narrowband filter at 1550 nanometers. And we generally have a loop speed of 10 to 20 hertz, and that's due to the current implementation of the algorithm. And the controlled modes are firstly the low wind effect modes, which is a mode basis specifically designed to correct for the low wind effect aberration. So it consists of piston, tip, and tilt modes for all 4 segments. And we also include the lowest 50 Zernike modes because we also want to be able to correct for low order quasi-statics. So in order to convince you that Fast and Furious really works, I'm first going to show you some data that we took when the low wind effect was quite severe. And this is without the Fast and Furious loop closed. So the Fast and Furious loop is open. And before I start, let's explain what we see here. So on the top left, you will see short exposure images of a star. And these are the images that Fast and Furious will use in the end to derive the wavefront. This is the time in hours, minutes, and seconds. This is the integrated PSF, and at the end of the video, it will basically give you an estimate of the long exposure PSF, and this is the average of the last 50 frames. So if I start the video, then you clearly see that the PSF is split up in multiple lobes, which is a clear sign of the low wind effect. And it also seems to jitter around a little bit, but this is due to the alignment algorithm that I use, and it tries to align the brightest lobe to the center, and sometimes this changes. So this is when we do not do anything about the low wind effect. And in the next video, which was actually taken just before the previous video, so this data set, in this data set we actually close the loop. And then you see a great difference. So this is the DM correction derived by Fast and Furious. And you see here a very clear step in phase along the spiders. So this is where the central obscuration is. And you actually see also the wind direction moving a little bit as the phase changes. So, and as you can already see, is the long exposure PSF looks a lot better than in the open loop. So if you want to quantify this, is the long-term PSF in the open loop. So you see that the PSF is quite distorted. You see a few lobes and the strill is 56%. And when we close the loop at Fast and Furious, the strill, it raises by 17% to 73%, and the PSF looks much more symmetric. So this shows that Fast and Furious was able to correct for this. So we also wanted to test this on longer time scales. So the video that I'm starting now is actually 10 minutes of Fast and Furious running shown in only 1 minute of video. And the interesting thing here is that you can see is that the low wind effect is evolving. So you basically see the wind direction, you see it changing over time. And as you can see, at the Subaru telescope, the M corrections to correct for low wind effect seem to be stable for quite some time, which suggests that the low wind effect, the time scale of the low wind effect, is a lot longer than we will see at the VLT. But this is something for later in the presentation. And as you can see, during this entire 10 minutes, the PSF, especially the long-term PSF, seems to be very stable. It's almost the same as what we had in the previous test. Okay, so this shows that Fast and Furious is able to maintain stability over long periods of time. Another interesting thing is, which was during another observation run a while back, is we were running Fast and Furious in near infrared, but simultaneously we were also recording PSFs in the optical. So in principle, if you're correcting, so these are shown here. Here the Fast and Furious loop is open. Here we close it. So this shows that when we close the Fast and Furious loop, we do not only provide a better correction for the near infrared, but we also improve the PSF in the optical. So we basically serve the entire instrument. So as to quantify these results again, this was from the last video. So this was the near infrared PSF when Fast and Furious was an open loop. So you can see that the strill is around 58%. When we close the loop, PSF becomes more symmetric and the strill raises by 5%. And in the optical, we see something similar. First, you have a strill of 13%, and then when we close the loop, Fast and Furious raises it to 20%. So what have we learned about the low wind effect at Subaru? Now, first of all, time scales. So at the VLT, Julien Milly, he determined that the typical time scale of the low wind effect evolution was around 1 to 2 seconds. But here at the Subaru, as for example shown in this video, it seems to be much longer. So we need to still do some more careful analysis to actually put a good number on this, but it seems to be longer than 4 seconds. So what could the cause be for this? First of all, or the only thing that I'm going to talk about is that the dome of the VLT is quite different from Subaru. So the VLT has relatively a lot of space around the dome. So basically the wind can come from every direction and it can change quickly. But for the Subaru, it's basically packed between 2 walls. So it could be, we still have to look into this, it could be that this forces the wind speed to only take a few modes basically that will remain stable for longer times. So this could be a reason for this. Another interesting thing is the morphology of the low wind effect. So when we take a look at a phase map derived by Zelda at the VLT, then you see the spiders here, and then you see the phase step over a spider and a phase gradient in only a few of the segments. So at SCExAO, when we look at the typical correction by Fast and Furious, we see phase gradients in every segment, not only behind spiders. So probably the reason for this is the difference in the top ring structure. So at the VLT, the M2 is raised above the top ring. So that means that only the spiders are basically dividing up the pupil. And if there is any low wind effect happening at the ring, it will be like a phase gradient over the entire pupil, which is something that can be measured by the wavefront sensors. But at Subaru, it's quite different. Then the M2 is in the plane of the top ring. That means that if you have any phase gradients, they will be broken up across the spiders. So that means that at Subaru we will get a low wind effect not only from the spiders but also from the top ring. So future work. So currently we run Fast and Furious in the near infrared, and we improve the optical, but we would like to do it vice versa. We would like to use the optical to derive the corrections such that we can do coronagraphy or other science in the near infrared. Together with Romain, we have been looking into if Fast and Furious corrections by Fast and Furious can improve kernel phase measurements and also any measurements with shape pupil. And we've been also looking into running Fast and Furious with the vector APP chronograph. The vector APP creates multiple PSFs. 2 of them have a dark hole where we can do exoplanet science or disk science, but there's also a third PSF in the center, which is basically the regular PSF of the instrument. And we can actually already on Sky, we have run Fast and Furious on this and it seemed to be successful. And then finally, we are also working together with people from keck to actually use Fast and Furious there to provide low order static calibrations. So to conclude, Fast and Furious is an easy to implement but powerful focal and wavefront sensing algorithm. We have successfully deployed it on Sky and corrected the low wind effect. And we have found that the low wind effect seems to have longer time scales at the Subaru compared to the VLT, and that the pupil plane phase morphology is different due to the top ring, also adding to it. So thank you for your attention, and I'll leave you with another video of Fast and Furious.
Great, thank you so much, Steven. That was very interesting. Looks like we have a few questions already coming in on the Slack channel. So the first one from Benoit is, how sensitive is the method to residual turbulence, and would it still be working in a regime of lower SR?
So what was the last part of the question? I couldn't.
Would it still be working in a regime with lower strahl?
Yeah, so that's a good question. So actually the first time that we tested Fast and Furious was in a lower strahl regime. So the example that I showed here, we had a strahl of around 70% when we corrected for the low wind effect. The first tests that we did were actually in a lower regime where the strahl was ranging between 30 to 50%. So during this, what you see here are long exposure PSFs. So this is when Fast and Furious closed loop. This was with open loop. So you see the symmetry here, and then again a closed loop PSF. And during this time, the seeing was degrading. So the corrections became worse. And it shows that we can still improve the symmetry of the PSF. I mean, it was hard to see any strahl improvements because the atmosphere was messing everything up. But we do notice that when we run with a more turbulent atmosphere, that the effective gain of the algorithm goes down, because basically you have this changing atmosphere that the algorithm is responding to, and only the static things will be corrected but slower. I hope this answers the question.
Okay, thank you. And then we have a couple more minutes, and it looks like we have another question online from Cedric. It says, what is the approximate amplitude of the differential pistons that you're able to correct?
I do not know by heart, but what I can show that is probably interesting is if I go to so we wrote a paper about this. I'm gonna just pull it up. So we did a test where we, on the DM, we introduced low wind effect modes with increasing peak to valley amplitude. And we made a nice plot about this. Let's go down. I should have put this in my presentation. So what you see here is the peak to valley wavefront error. It goes from 0.4 micron to almost 2. And this is the strahl as function of as amplitude. And this is before correction, and this is after correction. So what this shows is that we, over a wide range of low wind effect amplitudes, we can correct it.
Okay, thank you.
This answers the question as well.
Let's see, and Mamadou, I think we still have one more minute. So I missed a question from Scott Will. He says, Steven, is it possible to use Fast and Furious to correct high order wavefront errors in chronographic images? Or is it just practically difficult due to SNR issues, etc.?
I think it will be practically very difficult on Sky to do this. In principle, there should be no reason not to. Because if you run without noise, then you can probably correct PSF until 10 lambda over D or something. But at least what I've seen at SCExAO, it's on Sky it is very hard to do because you have a limited signal to noise, and things change very quickly at higher spatial frequencies.
Okay. And last one in our last minute from Ariel, it says, are the differential pistons caused by the low end effect small enough to be compensated in the optical, reference to wavelength wrapping?
Yes, I think so.
Okay. And okay, so it looks like we are out of time. Thank you so much, Stephen. I'd like to tell you that we do have a specific channel for each session. So Stephen and future speakers, if we don't get to your questions during the session, the speakers can go and answer these questions in the individual channels. So thank you very much, Stephen. That was a great talk. I think next